Hi everyone, thanks again for joining AWM Pitt Grad Seminar. Our next speaker is Valentina Bais. She's a PhD student from International School for Advanced Studies, Italy. Her topic today is on Stiefel's parallelizability theorem for closed three manifolds. You can go ahead, Valentina.
Thank you very much. I'm going to share my screen. Do you see something?
It started. So let's. It's black right now.
No,
Oh yeah. Now I can see.
Okay, you see. Okay, perfect. Okay, thank you very much for the invitation and for organizing all of this. It's a really nice initiative, in my opinion. So today, I would like to talk about a theorem that I particularly like. It is the Stiefel's theorem on parallelizability of closed orientable three manifolds. So my aim for today is first of all discuss the statement of this theorem. And in particular, I would like to begin by discussing the notion of parallelizability in the context of smooth and dimensional manifolds. And then I would like to move to the three-dimensional case, discuss Stiefel's theorem. And in particular, I would like to give a sketch of a new proof I developed with my master advisor, Daniele Zuddas, for my master's thesis. As you said, I'm from SISSA, but last year I was a master's student in Trieste, but at the University of Trieste. And as you can see, I have a quite nice picture in this first slide, which would represent the main tool that we use to attack this problem. Namely, this should represent a closed orientable three manifold M3 as a union of two pieces. And this is called the Haga splitting, and I will give the definition in the following. This was just to give a flavor of. Okay, so let's begin with the statement. The statement is the following: let M be a smooth closed orientable three manifold, then M is parallelizable. Well, this statement was first proved by Stiefel in 1935. And for me, closed means compact, connected, and without boundary. And I've stated the theorem this way because this is what we proved using our technique, but this holds even with our manifold is not closed, and even if we have boundary. And this result was proved by Stiefel, but nowadays we can find in literature several quite easy proofs of this statement using different techniques. I've put many in the references at the end, and maybe I will tell you what are these authors. And I will bring our proof. And so let's begin by defining parallelizable manifolds. So let M be a smooth and m-dimensional manifold. Then we say that M is parallelizable if its tangent bundle Tm is a trivial bundle, which is equivalent to say that we can find on this manifold M vector fields which are everywhere linearly independent at any point. And if you think about it, if we take such M vector fields, these give us a trivialization of our tangent bundle. And often one calls such an M tuple a parallelization of the manifold or a frame field. So at this point, one could ask, are all manifolds parallelizable? And the answer is no. First of all, if we take, for example, an orientable manifold, then this manifold cannot be parallelizable. For instance, let's take a frame field. If we have a frame field and orient this frame field, this induces an orientation of the manifold. So every non-orientable manifold is not parallelizable. So the best we can hope in the three-dimensional case that if we have an orientable manifold, that this may happen to be parallelizable, and this indeed is the case. There is a less trivial obstruction to parallelizability, which is the Euler characteristic. Indeed, if a manifold is parallelizable, that it has a vector field which is never vanishing, and by a theorem which is due to Poincaré and Hopf, this implies that the manifold needs to have trivial Euler characteristic. And so this is another obstruction, and this will help me to discuss the case in very low dimensions, just to give a flavor. Indeed, in dimension 1, the problem is trivial. because every orientable compact one manifold is just a one sphere S1, and we can find a parallelization, which is another vanishing vector field. But in dimension 2, the problem is not trivial. Indeed, if we take a compact orientable surface, then there is a theorem that tells us that we can classify all of them, and there are all the surfaces with bound donuts with G holes, namely the orientable surfaces of genus G. And we know very well also how to compute the Euler characteristic of such surfaces. Indeed, if M is our surface, the Euler characteristic of M is exactly equal to 2 minus 2 times the genus of the surface, which I have denoted by G, which is trivial if and only if the genus is 1. So we have hope just to parallelize the two-dimensional torus, which indeed we can do just by taking the product of the parallelization of S1. So we take one never-vanishing vector field in the direction of the meridian, and another one in the direction of the longitude, and that's the parallelization. So in dimension 2, the problem is not trivial. So dimension 3 is very special. And again, if we go to higher dimension, for example, in dimension 4, we have other restriction conditions on manifolds for being parallelizable. Indeed, one can prove that for manifold is parallelizable if and only if the Euler characteristic vanishes. And one needs to have other two topological conditions, which I won't discuss. So as you go in our dimension, the problem is again highly non-trivial. So dimension 3 is really a strange dimension in this sense. So let's go back to dimension 3 and discuss our main tool, namely Hagar splittings. Okay, this is a nice result due to Hagar, which allows us to represent any closed orientable three-manifold as the union of two very simple pieces. Indeed, if we take any closed orientable three-manifold, this can be written as the union of H1 and H2, where H1 and H2 are two handle bodies of genus G. Namely, there are three-dimensional manifolds with boundary. In the other picture, we had the surfaces. The surfaces bound the handle bodies, simply. And formally, it can be defined as the boundary connected sum of G copies of the solid torus, D2 times S1. And moreover, we can ask these handle bodies to intersect exactly along their common boundary, which is an orientable surface of genus G. So this tells us that we can think of any closed orientable three-manifold as two copies of two handle bodies of some genus G, which are glued along their boundary in some way. Maybe this way is very complicated, but the pieces the manifold is made of are really simple. And such a decomposition is called a Hagar splitting of the manifold. And now let's notice a really simple but useful thing, namely that the three-dimensional Euclidean space is parallelizable by a trivial frame field. And we can embed the two handle bodies of the splitting in R3. So also then the bodies inherit a parallelization from R3. So in particular, every closed orientable three-manifold is made of two parallelizable pieces. Now the problem is whenever we start from two parallelization, trying to glue them in a nice way. And this is the strategy we try to use to solve the problem. And so now I will start sketching the proof. Okay, so we start from M3, which is a closed orientable three-manifold, and we take a Hagar splitting, which from now on we will suppose to be fixed. So M is the union of H1 and H2, where H1 and H2 are underbodies of some genus G, and we start by fixing two frame fields of H1 and H2 respectively, which I've called P1 and P2. And so P1 and P2 are two triples of the everywhere linearly independent vector fields on H1 and H2 respectively. And now we would like P1 and P2 to agree on the intersection of the underbodies, but in general, of course, this is not the case. But anyway, in any case, we can try to compare P1 and P2 on the intersection of underbodies via a matrix valued continuous map, which I've called T, that sends every point X on the orientable surface of genus G, which is the intersection of underbodies, into a matrix, which is the change of basis matrix between the two parallelizations P1 and P2 evaluated at that point P. And these are all 3x3 matrices with coefficients in R, invertible, and we can suppose that they are all of positive determinant. And notice that P1 agrees with P2 on this intersection if and only if T is equal to the constant map with constant equal to the identity matrix. But anyway, even if T was not exactly this constant map, but was just homotopic to this constant map, we could make a trick, just take a Collar neighborhood of the orientable surface of genus G inside the manifold M, and use this Collar neighborhood in order to modify the two parallelization using homotopy between T and this constant map and make them agree in the intersection of the two underbodies. So our aim would be trying to find parallelization such that the associated map T is null homotopic. Okay, so we can change P1 and P2 to new parallelizations, which we have called Q1 and Q2. And how can we do it? We can do it via essentially changing basis. Namely, we can choose two matrix valued maps, which I've called C1 and C2, each one going from the respectively underbody into the general linear group of 3x3 matrices, real valued matrices with positive determinant. And at every point, these CI represent the change of basis matrix between the parallelization P1 and the parallelization Q1 and P2 and Q2 respectively. So our new aim is finding these maps C1 and C2, which represent the change of basis between the parallelizations PI, which were fixed at the beginning, and the new ones, just that the new change of basis map on the intersection of the underbodies is null homotopic. I have called this map T prime, and since both Q1 and Q2 can be represented, can be expressed in terms of the original parallelizations and this change of basis map C1 and C2, also T prime by simple computations can be represented by this pointwise product, where this dot represents pointwise the matrix product. So essentially T prime is completely determined by T, which was fixed by the initial data of the Hegel splitting and of the parallelization of the underbodies, and by these two maps, which we are free to change and to choose. So at this point, some algebraic topology comes into play, and one can prove that this map T prime is null homotopic if and only if it induces the trivial homomorphism between first homology groups with the two coefficients. And okay, I didn't write the proof, but essentially what one has to do is the following. First of all, you prove that this map is null homotopic if and only if it induces the trivial homomorphism between fundamental group, and then use the fact that the first homology group with coefficient Z is the abelianization of the fundamental group, and then you pass to the two coefficients, using the fact that here the fundamental group is Z2, since you can deformation retract this general linear group onto SO3, and SO3 is essentially RP3, which has as fundamental group Z2. Okay, so to prove our theorem, it is just enough to study this induced map T prime star. Yes, by T prime star, I mean the induced map by T prime between first homology groups with coefficients in Z2. And so to get our aim, we just want to find C1 and C2 in such a way that this map becomes the trivial map. Now notice the following, that on the left, we have the first homology group of the orientable surface with genus G with coefficient in Z2, which can be proven to be isomorphic to Z2 to the power 2G. And as a basis, we can choose, for example, what is called the symplectic basis made of all the meridians. So we have G meridians and G longitudes for the orientable surface. And as I told you before, on the right-hand side, I have just Z2, because the first fundamental group of this general linear group is Z2. By taking the parallelization, we get again Z2 because Z2 is already abelian. And by taking reduction by 2, we get again Z2. So this is the setting. And let's note two things. The first one is that from this expression, one can prove quite easily by using some computation that in this expression we have the pointwise the matrix product, and when we pass to the homomorphism between fundamental groups, the product becomes a plus, where the plus indicates the operation in this homology group, and here we have an inverse which becomes a plus because Z2 minus a plus are the same essentially, and so we have a quite easy expression for T prime star in terms of T star, C2 star, and C1 star. And moreover, these two are both vector spaces. So we are dealing with a linear map between vector spaces. So this T prime star is 0 if and only if it is 0 evaluated on any basis of the vector space in the domain. So what we have done is finding a basis of the first homology group of the orientable surface of genus G with coefficient in Z2 in such a way that T prime star computed on each small element of this basis is 0. And note the following, that T prime star evaluated on an element of the basis is this expression. For example, if we fix a basis alpha 1, alpha 2 G, and evaluate T prime star on alpha I, the expression we get is C2 star applied on alpha I plus T star on alpha I plus C1 star on alpha I. And these are all numbers between 0 and 1 in the Z2 group. And T star alpha I was fixed by the initial data, so we can't change this. But we are able to choose in principle these two. So what we have done is, first of all, building a nice basis in such a way that we could choose in a nice way C1 star and C2 star. Namely, if T star of alpha I happen to be 0, we've chosen these two maps in such a way that also these two values happen to be 0. And whenever T star of alpha I is 1, we are able to choose C1 and C2 in such a way that one of the two values is 1 and the other one is 0, or vice versa. And so in this way, using these two maps C1 and C2, we can build the nice parallelizations Q1 and Q2 that up to some adjustments glue together in a nice way and allow us to build a global parallelization of our manifold M. Okay, this is just a flavor, it's not a complete proof, but I just wanted to convey what was the initial idea behind all of this, and also because I think it's a really nice result. I mean, the only other dimension which this is trivial is the dimension 1, so it's quite surprising. I was quite surprised when I discovered this. And so I have 5 minutes, but I think I'm already over. I just wanted to show you the references and say something. Okay, the first reference is, our paper in which we can find the detailed proof. And then these are the other bare hands proof that you can find in literature. Namely, you have this paper by Benedetti and Liska, which is called Framing Three Manifolds with Bare Hands, in which you can find other 3 proofs. 2 of them use Hegel splittings, but in a different way. And one of them uses almost just algebraic topology. Then there's this other paper by Durst, Geiges, and Gonzalo and Kegel, which is called Parallelizability of Three Manifolds via Surgery. And this contains other 2 proofs. One of them also is via Hegel splittings. And then I also put the original paper by Stiefel, which is called Richtungsfelder und Fernparallelismus in n-dimensionale Mannigfaltigkeiten. And just an interesting fact, this is also the paper where the Stiefel-Widner classes of topology were first defined. And here also he proved this fact that all closed orientable three manifolds are parallelizable by using more, say, advanced techniques, namely Stiefel-Whitney classes. And I think I'm done. Thank you very much.
Thank you so much for the talk.